Here we consider the center of mass of two particle system. How to find the center of mass of two particle system? To understand that, let us consider two particles here, one of mass m1 and another of mass m2. Now, between these two particles, there will be interaction coming, and I am taking these two together as a single system. But in order to analyze the movement of these mass particles properly, you have to consider a coordinate system so that you can have the position of each particle. So, I will be drawing a coordinate system here. Yes. Say coordinate system here, origin. And from the origin, now you can define the distance to the mass m1. Distance to the mass m1. So this distance, I could say it is the position vector for mass m1. R1 is the position vector of mass m1. So actually, taking that vector, we can identify where the mass m1 is from the origin. Like that, if I take m2 and find the distance to m2 from the origin, this gives the position vector r2. So r2 is the position vector of mass m2. So go to the meaning of position vector. Now you can identify the movement of mass m1 and m2 in this Cartesian coordinate system clearly, because from the origin where it is, it's now understood. Now if I take these two together as a single system and if I apply force F on it, I am applying a force F external. I am applying a force F on this system. Now as I apply force F on this system, the mass m1 and m2 will be moving according to the force F. Now there will be a force between m1 and m2, and I told you there is the internal force that is cancelling each other, and therefore application of this external force produces a force on m1, let it be F1, and force on m2, let it be F2. So F1 and F2 are the forces experienced by mass m1 and m2, where I apply an external force on the system. Okay. Now at this point, we are now taking Newton's second law, that force F is equal to rate of change of momentum of the particle. So as I take it like that, I can take here it as d by dt of p1 plus d by dt of p2, where p1 and p2 are the momenta of mass m1 and mass m2. And therefore, I can split this as d by dt of m1 v1 plus d by dt of m2 v2, where v1 and v2 are the velocities experienced by mass m1 and m2 because of the force f1 and f2 acting on it. Clear? Now I can take this in another form, that m1 into d by dt of v1 plus m2 into d by dt of v2. Like that, I will be moving to m1 into d by dt of v1. I can take it as d by dt of r1, position vector of r1. And here I can take it as m2 into d by dt of position vector r. Understood? So we have come up to where the position vectors, how they are connected to the forces F1 and F2. Clear? Now, as we continue with this, we can have the equation rewritten as m1 into d square by dt square of r1 plus m2 into d square by dt square of r2, or I could rewrite this as d square by dt square of m1 r1 plus m2 r2. I could write. Alright? Because m1 and m2 are the constants, only r1 and r2 will be varying. Therefore, you can rewrite this. And as we continue, we will be taking the left side of this one, that F external will be equal to mass of the whole system, that is m1 plus m2. Mass of the whole system is m1 plus m2, and which is equal into d square by dt square of RCM. So what is RCM? Let us say, as we consider m1 and m2 connected as a single system, its center of mass will be falling somewhere on the line joining the two. I don't know where it is, but on the line joining the two masses. And here this the center of mass is coming from the system. Then, if that is the position of the center of mass, then I can assume this as RCM, the position vector of center of mass of m1 and m2. And at this point, the whole mass is concentrated. It's supposed to be concentrated. So mass at this point we can assume it as sum of m1 and m2. So it's coming like this. So the whole force F is directly applied onto this m1 and m2. The system will behave exactly as before. This is what we see. So when I apply the external force directly onto this, the effect is same, and therefore that force can be written as m1 plus m2 into d square by dt square of RCM. Now when I compare these two, you can get m1 plus m2 into d square by dt square of RCM will be equal to d square by dt square of m1 plus m1 r1 plus m2 r2. Correct. Or if I rewrite this, taking this m1 plus m2 inside, and I get it as d square by dt square of m1 plus m2 into RCM will be equal to d square by dt square of m1 r1 plus m2 r2. So the derivative effect on left and right is same, that is the second derivative is coming d square by dt square the same way. Therefore, I can ignore that on both sides and we get the condition as m1 plus m2 into RCM will be equal to m1 r1 plus m2 r2 and therefore RCM, the position vector of center of mass, therefore will be equal to m1 r1 plus m2 r2 divided by m1 plus m2. So this is the equation you can use to find the position vector of two particle system m1 and m2. And this equation can be extended to n particles also by taking RCM equal to m1 r1 plus m2 r2 plus m3 r3 plus etc plus mn rn divided by m1 plus m2 plus etc plus mn. So any number of particles you can use the same equation extended. Okay. So very important. The derivation side we are using only the momentum conservation and all those things, and we are reaching to this particular point. Now the variation of this formula you can see in the next